Hi everybody, in this video we will talk about pi groups and the concept of similitude, and both of these are relevant for the biotransport class. So let's start with pi groups. So pi groups basically capture the notion of natural processes, and they do it independent of any system of units that we as humans may impose on them, right? So the way you create pi groups is you're going to have two or more entities, and you can combine them in any way that you like in the numerator and the denominator, but you have to make sure that at the end of the day, the units in the numerator and denominator need to cancel out. Okay, so basically to make sure that they're dimensionless. And in the context of BMED 3310, sometimes you may be asked to prove, on your test whether or not something is a valid pi group. So they'll give you, a whole bunch of quantities multiplied together, and then they'll say, okay, this is a pi group, right? Let's say, for example, they said A, and A could equals, a couple of things that you multiplied or divided together, and they say this is A. Prove that A is a valid pi group. So the way you would do it is you're going to look at the quantities that are, that constitute A, right? So A could be made up of B, C, and D, for example. So you're going to put in the appropriate units for B, C, and D, and the way they have it in your in the setup of the pi group, right? So if it's in the numerator, the exponent for the dimension is going to be positive. If it's in the denominator, it's going to be negative, etc. So once you do all the math, you're going to see that your imported dimensions of interest, right? So we see that M, L, and T here. So that's representing mass, length, and time. And once you cancel the units out, you're going to get M to the 0, L to the 0, and T to the 0. Now, for those of you guys who are taking 3310 right now, you may be familiar with some of the pi groups that are pretty important in this class, such as Reynolds number and friction factor. Okay, so how do you actually generate these pi groups? So for that, that's where your Buckingham PI Theorem comes in. And basically, this theorem, it's just a formal way to generate pi groups. So you're going to be given a certain number of variables, and you have to, you read the question carefully. Most of the time in 3310, they'll actually give you almost all the variables of interest. Like they'll tell you, okay, pressure is relevant, or, viscosity or density, volume, etc. Things like that are important, and usually they'll leave one or two of these types of variables kind of for you to sort of think about and kind of come up on your own, right? So most of them are going to be explicitly mentioned, and one or two you have to think about it, and implicitly they're telling you, but you have to kind of think about it and understand it and then come up with it on your own. So basically what you're going to do, the way this theorem works is you're going to create a matrix. Okay, so it's going to be a P by N matrix. So you're going to have P rows, okay, and N columns. And P represents the number of dimensions of interest that you have. And in 3310, we just care about 3 of them. Okay, so we just care about mass, length, and time. Okay, so that's going to be the rows that you have. And then in your columns, you're going to have the variables of interest. And that actually just varies based on the problem that they've given you. Usually you'll be given like a paragraph or two, and then most of them will already be explicitly given to you, that we care about the pressure, we care about the Young's modulus or the viscosity, etc. And then so what you're going to do is you're going to write all of that out, and then represent the appropriate dimensions for the ML and T. So just the exponents for those. Okay, and we'll do an example in a minute, so it'll make more sense once we get there. And you can also compute based on your matrix. You can compute I, which is representing the number of pi groups. So I is going to be equals to N minus R. So N again is that number of variables, your columns, right? So that's based on your problem statement. And R is the rank of a matrix. So if you think back to your Calc 2 class, right? When you have matrices, sometimes your columns and rows, they're not independent, right? So you can combine one or two of the other rows and maybe multiply it by something or add them together or something, and you can get another row or another column out of it. So that's not independent, right? So that concept of independence becomes really important. In this case, we just care about the rank of a particular row, right? So if you have a degenerate matrix, meaning that all rows are not independent, then you have to make sure that your R is appropriate. Okay, so it's not always going to be 3. In many cases, it is 3 in 3310, but it could be different. So just wanted to make sure you guys are aware of that. Okay, so there are several steps to generating pi groups. I'm going to briefly just mention them here, but they're going to make more sense when we do the problem in the next couple of minutes, okay? So first, as I mentioned, what you're going to do is you're going to read your problem statement carefully, and you're going to write down the relevant variables, and then you have to think about it. You have to think about what are their dimensions, right, in terms of your mass, length, and time. Like for example, if I was to tell you, okay, density is an important variable of interest here. So what is density, right? Density is rho is equals to mass over volume, right? So we're going to have mass over L cubed, m over L cubed, right? So m is going to be raised to the first power, and your L, which is the length, that's going to be raised to the -3 power, right? Because it's in the denominator. So things like that. So that's what you're going to do. All the variables of interest that you have in that problem, you're going to distill them down into exponents. So what is the exponent for m? What is the exponent for L? What's the exponent for t? Okay, and then you're going to use these together to create your matrix. Okay, and then you're going to, so that's, when you start using your Buckingham PI Theorem. And then you're going to compute your I, or how many pi groups you can generate. And then what you're going to do is you're going to pick a core group of variables. So you can pick 2 or 3 variables, and you just have to make sure that it's not a pi group by itself. Okay. And once you have determined your core group, what you're going to do is you're going to take that core group and you're going to multiply it with one of the other variables that you did not use to create your core group. Okay, so you're going to multiply these together, and then what you're going to do is you're going to substitute in the dimensions for each variable in your pi group, and then you're going to solve that systems of equation for mass, length, and time. You're going to set it, all of them equals to 0. Okay, and then you keep doing this process until you have generated all of your pi groups. Okay, so let's do an example. So here we're told that the pressure drop per unit length in turbulent flow, which we can represent as delta P over L, is known to depend on the pipe diameter D, the pipe wall roughness epsilon, the fluid velocity V, and the fluid viscosity and density, which are the mu and the rho respectively. So what pi groups can be formed in this problem, right? So if you go back to the steps here, right, first we have to write down the relevant variables and their dimensions. So in this case, as I mentioned, they actually usually always mention almost everything except 1 or 2. In this, actually, this example is not too bad, so they've actually already given you everything explicitly. So notice here we have a delta P over L. That's one of the variables of interest. We have a D, we have an epsilon, V, mu, and rho. These are all the relevant variables of interest here, right? So what we do is we just write that down, tabulate it, and then we think about what are the dimensions for these in terms of your M, L, and T, right? So if you look at density, like that example I mentioned, right? Density is mass per volume, so you're going to get M over L cubed, right? And when you just bring everything to the numerator, the L's exponent is going to be negative, right? And you're going to keep doing that. So your diameter, that's a length. Epsilon, that's a length. Velocity, that's a meter per second. So meter, that's the L for the meter per second. Time units in the denominator. So when you bring it back up, you're going to have a -1 in the exponent. So that's basically what you do. Okay, and then now what you're going to do is you're going to create your matrix, right? So so now we're trying to use the Buckingham PI Theorem. So what I did was I took my dimensions M, L, and T, and I put that for the rows, and all of these variables that I came up with, I put that for my columns, right? Now what I need to do is I need to look at the M, L, and T and the exponents for them in this side, and then I'm going to just put just the value for the exponent here. So if it's a negative, I need to make sure I put a negative there, right? So again, if you look at density, that's the one most of us are familiar with. So so now what we're going to do is we're going to say, okay, M over L cubed. So we have a 1 for the M, right? Again, we're looking at the row. And we have a -3 for the L, right? Kind of coming from here. So that makes sense. And notice we didn't have anything to do with T, so we just put a 0 for T here, right? So that basically that's what we're going to do. We have our variables, we have our dimensions. All the exponents, we're going to we're going to copy it from here to in this matrix format, right? And then what we can do is after we have this matrix generated, now you're going to look at how many pi groups you can generate, right? So you have I, that's representing your number of pi groups. What we're going to do is we're going to subtract n, which are the total number of variables of interest, right? So if we count these, we have 6 of them here, right? 6 of these, and then we're going to subtract it with R. In this case, all the rows are independent of each other, right? So our rank, we're going to have a full rank here, so R is 3, right? So when we do 6 minus 3, we now know that we're going to have 3 pi groups. Now, before we get there, one clarification I do want to make. Let's say I have a pi group, right? I have a pi group, let's say A again, right? Now, the thing is, I can generate technically an infinite number of pi groups, right? So if you think about it, okay, I have A as a pi group. Well, 2A is also a pi group, right? A squared is also a pi group. Square root of A is also a pi group. A over 2 is also a pi group, right? But the thing is, they're all they have that essence, which is that A, which is that initial pi group, and then they're just kind of, you're just scaling it up by a certain amount, right? So when we say that there are 3 pi groups, we're saying that there are 3 independent pi groups. There are 3 unique pi groups, and then you can generate an infinite number of redundant pi groups that are going to be essentially the same thing at the end of the day, right? So I just wanted to make sure you guys are aware of that as well. Okay, so now we know that there are 3 pi groups, so let's start generating them, right? So first, before we get there, we're gonna have to come up with our core variables. So in this case, I just picked, D, V, and rho, right? So to make sure that we picked a good core group, remember I mentioned, the core group itself cannot be a pi group, right? So the core group itself, when you multiply all of them together, you can't just get a 0 in the M and the L and the T, right? So for all of these variables, so if you look actually in the matrix here, so you can just do a quick check. So if I pick rho, V, and D, right? I sum up the exponents here for the M. So I'm going to do 1 plus 0 plus 0, and that does not equal 0. That equals 1, right? So that's good. And you can also do the same check for the L and the T, but basically, if you're not getting M to the 0, L to the 0, and T to the 0, then you're good. Okay, so we have our core group now, and now what we're going to do is now we're going to start generating the pi groups. So what we're going to do is we're going to say our pi group is equals to our core group, so that's represented in the red right here, right? Each variable in my core group, so your D, V, and rho, so again, in the red quantity here, we have D to the A power. We're going to raise these core variables to a power, A, B, and C, right? So we're going to say D to the A power, V to the B power, rho to the C power. Okay, so that's my core group. And then in the blue, that's representing my choices for a variable that's not considered a part of my core variables, right? So basically I was left with 3 other variables after I chose my core variables, right? So I was left with this quantity, delta P over L. I was left with viscosity, and I was left with epsilon, right? So I could have picked any of these 3. In this case, I just picked the first one. It really doesn't matter. We just care about what the pi group actually is. It doesn't matter which one you say pi 1 or pi 2 or pi 3, okay? So now we have that. And now what we're going to do is we're going to actually put the dimensions for each of these quantities, right? So my dimension for D, the diameter, that's just a length, right? So I just did L to the A power, right? Now V, that's velocity, right? So that's meter per second, L to the T minus 1. So it's the whole quantity raised to that power, right? So notice so basically I'm saying now we have L to the B and T to the minus B power, right? And you're going to do that for all of them, right? So put in the values for this and for that. And what you're going to do is now you're going to make all of this equals to so again, we're trying to generate a valid pi group. We're going to have M to the 0, L to the 0, T to the 0, since pi groups are dimensionless, right? So now, once we have this set up, now we can actually do our system of equations, right? So if you think back to algebra, what you're going to do is you're going to say, okay, wherever I see an L, I'm going to sum up all the exponents, and I'm going to make that equals to 0. So I see an L here. Okay, so I have, actually, let's start with M first. So M, let's see, where do I see an M? I see an M here. So I see a C, M raised to the C power. So I see a C, and I see a 1 here. So I see C plus 1 needs to be equals to 0. That's my equation for M, right? And then when I come to L, I see a whole bunch of L's here. So I see an L to the A power, and then I see an L to the B power, and then I see an L to the minus 3C power, and then I see an L to the minus 2. So I'm just going to sum up the exponents for L, right? So I see that A plus B minus 3 minus 2, and then again I set it equals to 0. And then for T, I do the same thing. So I see that, okay, we have a T to the negative B, and then I see that we have a T to the minus 2 power, right? So we're going to say minus B minus 2 is equals to 0 for T. And then we're going to get the values for what these, what the A, B, and C represent, right? So now from doing this math, we're going to see that our A is equals to 1, B is equals to negative 2, and C equals negative 1, right? So again, oops. There we go. Okay, so now my A, B, and C, I've written it again here. Now what we're going to do is, notice how we said pi 1 is equals to D to the A power, V to the B power, rho to the C power, right? So now what I'm going to do is I'm going to take these core group quantities, and I'm actually going to substitute in the values for A, B, and C, right? So A was 1, B was negative 2, and C was negative 1. So D to the 1, V to the negative 2, and rho to the negative 1. And then again, I'm still multiplying by this extra remaining variable that was not part of the core group. And then I keep doing this multiplication, simplification, right? So if I have to move the V, for example, in the denominator, which I did here, right? Same thing for my rho. Again, I put it in the denominator. So I make sure that everything, if it needs to be in the numerator, it's in the numerator. If it needs to be in the denominator, I put it in the denominator, right? Now, it just turns out in BME 3310, this quantity actually is friction factor over 2, okay? So that's our first pi group, basically. So, you could have left your answer off at just this part, and that's fine. But I just wanted to put this here for your reference, that it's equals to F over 2. Okay, so that's our first pi group, right? So hopefully you guys are kind of understanding how we do this. Now the next pi group, how would you do it, right? So the way you would do it is you're going to take this core group again, and then you're going to substitute in a different variable that you did not already, generate a pi group with. So we're left with a mu and we're left with an epsilon. So you just substitute in one of the two, and then you keep doing this again, right? Again, put your appropriate number, your appropriate dimensions in here. Say that it equals to m to the 0, l to the 0, t to the 0. Create your system of equations and then solve. Okay, so I'll leave that as an exercise for you guys, but just to make sure you guys can check your work, you should get that pi 2 is equals to epsilon over d, and your pi 3 is equals to mu over rho vd, and just for your reference, that's just an inverse of the Reynolds d. Okay, now another concept that's important when we talk about pi groups is this idea of similitude, right? So, that's basically referring to, scaling of transport phenomenon from one situation to another. So a good way to kind of understand this, I like to think of like some examples, right? So let's say that you wanted to design an airplane, right? Let's say you work for Boeing or some, airline company, and what you're trying to do is you're trying to save the amount of fuel that the plane takes to go from point A to point B. Or, you want to do it so, it goes there, goes faster, right? So it gets there from A to B in less time than it usually does, right? So you have this crazy idea. What if I design the wing shape a particular way, right? That I can get all the, aerodynamic and all the properties that I need to make sure that the plane will actually accomplish the goal that I want, which is, consume less fuel or get from point A to point B faster, right? Now think about it. An airplane is so big, it costs millions of dollars to create an airplane. Are you just going to test any random idea that you have out of thin air and then just spend the millions of dollars and to test that airplane wing, right? What if your idea is wrong, right? Then you're going to just lose all that money. So as you can kind of imagine, that's not usually how things work, right? So what you do is you're going to create a model of the airplane that's, 200 times or 250 times smaller, right? But that smaller model will have that design that you want, right? So if you were like, okay, we can just design the wing shape a certain way, or whatever, your design is, you're going to just make a really small model of that's more cheaper and affordable. And then you're also going to, your testing situation, you're also going to scale that appropriately and then see how your smaller airplane does, right? So if your idea is really bad, then you didn't waste millions of dollars testing this idea. And if your idea is good, then you can just validate it. Maybe you can validate it with another bigger model than your initial one. Maybe, it's only 100 times smaller now, right? And then you're going to test it, and then you keep doing that, and then you're like, no, we're actually onto something. This is a really good design. Then you're going to go ahead and spend the millions of dollars and create that airplane, right? And this also applies actually for BME as well. So if you think about, if you're trying to test, the action of a drug on certain animal organs, right? You may do the testing on a rat, or you may do it on some other animal that's bigger than a human, right? Like a giraffe or elephant or something. And obviously, depending on the animal size, their organ size is not going to be the same as that of a human, right? So if you realize that, the drug takes, let's say, 5 minutes to get its action done on the animal organ, the animal's lungs, for example, and that maybe the human lung is 2 times that of whatever animal you're testing with, then you may, it's safe for you to assume, okay, it's probably going to take 10 minutes in the human, right? But of course, you got to do animal studies first before you just move on to, human studies, right? So that's where this concept of similitude comes in. So in both of these situations, between your model and your actual, actual size of, that situation that you're trying to model, what you're going to do is you're going to say a certain pi group is the same in both of these situations, right? So for example, your friction factor is the same in both of them. And then what you're going to do is you're going to know one quantity in one of the, from one side of, whether it's in the model or the actual, and you're going to know another quantity in the other side of the equation, and then you're going to rearrange to solve for that quantity of interest, right? So let's look at a problem, and I think it'll make more sense to you guys. Okay, so this is a pi group and similitude. It's like a combined problem, right? So I know there's a lot of text here. So here, we're talking about a lung. So it's an elastic structure periodically filled by air. And this emptying and filling during the normal tidal breathing, it's driven by variations in pressure. And then, so on and so forth. We're told these are the different variables of interest. So the first part of the question is that there are 3 pi groups in this problem, right? And then we're told that show that this quantity, and this quantity are valid pi groups, right? So remember what I mentioned right when I started the video? I mentioned that to prove something is a valid pi group, all you need to do is you're going to substitute in the dimensions for f, dimensions for actually all of these variables, right? Make sure you scale it appropriately based on the exponent that you have. Oops, excuse me. And then what I'm going to do is after I do that, I'll see that the quantities in the numerator and the denominator are exactly the same. And I should get a dimensionless quantity. So I'm going to get m to the 0, l to the 0, and t to the 0, right? So if you do that for all three of these, you can prove that it's a valid pi group, right? Now, to help you guys out a little bit, I'm not going to solve the whole problem, right? But I'm going to do the first part, which is when you write the variable and their dimensions, right? So just to make sure you guys have something to check your work with, right? These are the variables in this problem, and I've written their corresponding dimensions, right? So all you need to do is put in the quantities, right? So for example, wherever I see a delta p, I'm going to put in this unit here, right? And then when I see an f, right, in this case, f is the frequency, inverse of seconds, so I'm just going to put that in as an inverse of seconds. So I'm going to get t to the -2 here in this case, right? And you just put in the appropriate dimensions. Make sure you pay attention to the exponents, and you should, after canceling everything out, you should get m to the 0, l to the 0, and t to the 0, right? Now the second part of this problem is what actually relates to similitude, right? So here we're told that, so you're doing an experiment. You're doing an experiment on the model, and then you're trying to figure out what it's going to be in the human, right? So you're told that if the pressure drop in the experiments on rat lungs was measured to be 4 centimeters of H2O, predict the value of delta P when you're going to do this experiment in the pleural space of human lungs, right? So, and we're told another important thing here as well, that, you may assume that the elastic modulus of the rat lung is the same as that of the human, right? That may not necessarily be true, but just for the sake of this problem, we're told that that's true. Okay, so remember what I said, when you do similitude problems, you're going to take one pi group that's common between both of these situations, and then you're going to say, of course the pi group is going to be the similar, but you just need to figure out which pi group, right? So like for example, in the last problem, they told you that there are 3 pi groups, right? So you just need to look at which variables of interest here that are being discussed, and then you just need to pick that appropriate pi group that has that quantity, right? So in this case, we care about this delta P, right? So we notice in these 3 pi groups, only one of them has a delta P. So we see that we're going to do something with this pi group, right? So what we're going to do is we're going to say the pi group between the model and the pi group between the human is going to be the same, right? So we're going to say this, right? So this is our pi group for the human case, and this is the pi group for the rat case. Okay, now what we're going to do is we're going to plug in any values that we are told and then rearrange for the variable that we are trying to solve for. So in this case, what I'm going to first do is, so here actually, so this is a little bit more simplistic example. So here, see, we're told that the elastic modulus of both is the same, right? So I can put a 1 in here for E of H and E of R because they're the same, right? And then I'm going to put in the value for the rat, for the delta P, which we're told, which is 4 centimeters H2O. In this case, the human case is going to be the same thing, right? They're both going to be 4 centimeters of H2O. But let's see if what if I change this problem a little bit? Okay, so now what I'm going to say, I'm going to say now they're not the same anymore. Okay, so I just made this number up. So we're saying that assume the elastic modulus of the rat is 2 times that of a human, right? So now what we're going to do, again, we're going to start up with this pi group, and then we're going to plug in the appropriate numbers. But before that, we're going to actually rearrange for what we were actually trying to solve for, right? In this case, that's the delta P of H, right? That's what we're solving for. So for the human case, all I did was I just rearranged this equation, so I solved for delta P of H, right? So I'm going to multiply the delta P of R and E of H, and then divide it by E of R, right? So I'm going to get this equation, and then I'm going to start plugging things in. So I'm told that the rat has an elastic modulus 2 times bigger than that of a human. So if a human one, we're going to say, let's say that's 1, then I'm going to get a 2 here for the E of R, right? And then the delta P of R, we're told that's 4 centimeters of H2O. So then I start plugging my values in, and I'm going to get 4 over 2 times 1. And then in this case, now I'm going to get 2 centimeters of H2O, right? And similarly, you can be given more situations, more testing that has been done, and you can be told that the model behaves this certain way, and maybe the actual thing is this much bigger or smaller than the model. Compute what it's going to be in the actual situation, and that's kind of how these similitude problems work. So I hope you guys find this video helpful, and thanks for watching.